May 19th, 2018. The Kuraray America chemical plant in Pasadena, Texas. The plant manufactures Eval, a copolymer made from ethylene and vinyl alcohol. Eval is used in food packaging and storage containers. Kuraray shut down the Pasadena plant on April 6th for a maintenance turnaround and to install various equipment upgrades. By May 18th, Kuraray operations personnel were taking steps to bring one of 4 reactors back online. The reactor, known as Eval Reactor 2, looked similar to the others, but had a lower maximum design pressure of 740 psi. The design pressure of the other 3 reactors was 1150 psi. The reactor already had liquid methanol and ethylene vapor inside as operators began incrementally raising the reactor system pressure. They did so by adding additional ethylene vapor. Pressure was raised in order to reach the target pressure necessary for the reactor to start up, while also checking for leaks. In the meantime, chilled liquid from the plant's newly installed refrigeration system was circulating through the reactor's heat exchanger. After 11:20 p.m., the reactor pressure, together with the low temperature from the chilled liquid, created conditions that allowed the ethylene gas in the reactor to condense to liquid. This caused the temperature in the reactor to decrease. Around 7 a.m. on May 19th, a supervisor noticed the low temperature in the reactor and instructed operators to stop circulating the chilled liquid through the heat exchanger. The reactor was surrounded by a heat transfer jacket, which uses water to control the temperature inside the reactor. To further help warm the reactor, Kuraray personnel periodically added steam to the jacket, increasing the temperature of the water. As the temperature of the reactor increased with each injection of steam to the heat transfer jacket, some liquid ethylene inside the reactor vaporized. This raised the pressure inside the reactor. By about 8:45 a.m., the reactor reached the target operating pressure of nearly 600 psi, but pressure continued to increase. Around 9 a.m., the pressure reached 640 psi, and the high-pressure alarm went off. A board operator responded by periodically opening a pressure control valve to send some of the vapor inside the reactor to a flare. The board operator was concerned about exceeding environmental emissions limits for the flare. As a result, he did not fully open the pressure control valve. He was also focused on other startup activities and did not realize the valve was not open as much as it needed to be to bring the pressure under control.
What comes to mind when you're seeing this at this moment?
You know, one thing that stood out was the supervisor who noticed, you know, temperature wasn't where it should have been, had to come in and tell, I'm guessing, the board operator to make the changes. What comes to my mind is, as they were starting this operation and throughout the operation, what were they looking at before startup, during the operation? Basically, what layers of protection, you know, did they have in mind? Did they know the design pressure of the vessel? Did they know the temperature and pressure operating parameters? Those are the kinds of things in process safety you've got to look at, keep in mind. Ideally, they're written down either in procedures or in some kind of, you know, checklist at a minimum. Did the board operators, did the operators themselves take the time to look at that, to look that up, to have that knowledge in mind, to know where their limits are from the process safety standpoint? And that's what having the right process safety culture and following the 4 pillars of safe execution are all about. Taking the time beforehand and make sure you know what your layers of protection are, you know where your limits are. Operationally, from the process standpoint, what should I look out for to know that everything is within limits, within safe limits, or I'm encroaching on something else? The other thing, of course, is, you know, working too many things at once. So very, very often It happens during startup equipment, after turnarounds. You've got multiple things going on, things that are part of normal operation, not part of steady state operation. So it's a very risky time period, but that's where process safety leadership is even more critical. Is the leadership giving you the space to be able to perform every one of your duties in a safe manner with the time needed to do all the things that I mentioned before, look at all your safe operating limits. That really is where leadership plays a big role. And if there's not a culture of process safety, a strong culture, you're going to be pressured to do as much as you can, not to speak up and say, wait, hang on, I can't do that yet. I need more time, because if the schedule is running the show, things might get overlooked. Like it looks like the operator overlooked how much that pressure control valve needed to be open. That's what comes to my mind so far.
Yeah. We haven't finished the video. This is obviously the first time that we're seeing this, but wonder, just like you mentioned, this deviation of essentially manually managing the pressure, if it is part of the procedure, right? It is actually, or was it something that was done kind of on the fly because we have to keep this unit running? And so thinking about, like you said, being able to have those conversations and being open and transparent about it as a concern when obviously there's an alarm going off. What does this actually entail? What does this actually mean? And at the beginning of the video, which I'm sure has to do something with it, this reactor in itself has a lower pressure rating than the other ones. It's a lot of culture. We can see, at least at this point, up to this stage, that there is normalization of deviation, right? We're thinking, hey, we'll do what needs to get done at the moment to keep the unit running as it should, right? So
exactly, and that's a slippery slope. Basically, it's just so critical that your process safety culture is strong, because you want to have the right reactions. What I mean, and no pun intended, this is reactor, but in the beginning, when, for example, it was noticed that the temperature, it looks like from the description of the video, the temperature was not really doing what it needed to be doing, right? First, they had to cool it down. Then they were trying to heat it up. So when those sorts of things start to happen, your reaction is critical. By your reaction, I mean both of the supervisor and of the board operator. What should your reaction be? If you've got too many things going in manual, like you said, with the valve and everything, it should really be a sign that you need to stop. You need to stop and say, hang on, we need a better plan. We've got too many things going on in manual. We need to take a moment, however long that may be, and regroup and figure out, okay, how can we do this again with our pressure control valve in auto? For some reason, we couldn't have it in auto. We had to do this manual. With our temperature being controlled, more automatically. It's that stopping and that regrouping that can make the big difference between something going wrong and you taking a little longer, but things going right. And so that right there is such a good example of process safety culture and leadership.
Yeah, or lack of, right? We gotta be, so the question here as a leader on the site is, are your operators, are your peers comfortable stopping the job? Are they comfortable raising the hand and just asking, does this really make sense?
Yeah.
Right.
And are you comfortable as a supervisor also stopping the job or telling your operators, okay, let's stop it? Or are you feeling pressure from your supervisors and up the chain? No, we've got to keep going. We're already behind schedule.
Pressure inside the reactor continued to climb. Shortly after 10 a.m., operators initiated the next step in the startup. At that time, a new board operator took over and noticed the pressure in the reactor was over 700 psi. But the operator did not recall that this reactor had a maximum design pressure of 740 psi. He thought it could withstand higher pressure like the others. Like the first board operator, the new operator only partially opened the pressure control valve, not realizing how dangerously close the pressure was to the reactor's limit. The partially open control valve was not enough to relieve the pressure in the reactor. Shortly before 10:30 a.m., the emergency pressure relief system activated. High-pressure ethylene vapor discharged from the reactor into the atmosphere. It was released horizontally toward an area where many people were working, rather than vertically to a safe location.
Wow. So many things to think about. Shift handover, due diligence, assuming that the equipment is rated for a certain amount. Again, normalization of deviation. And I guess, at this point, there's an alarm, but there's not an automatic shutdown around the pressure. I guess, there's a couple of, I don't know, the details around the engineering on this, but just an alarm, but what's up with that, right? And then obviously, besides the alarm, it's not, I don't know if it's being bypassed or the shutdown's being bypassed, but we're relying solely on administrative controls at this point that have not gone through proper due diligence. And so again, this comes back to process safety leadership culture, because if process safety is top of mind in your culture as a leader, as a peer, as an operator, as an engineer, there has to be conversations, right? Coffee room conversations around, hey, are we okay with this? Before the shift handovers ended, how was this assessed, right? How did we stop?
Yeah, was there a plan to control the pressure handed over at shift handover? Hey, we've got high pressure. We're trying to relieve it through the pressure control valve. Here's the plan going forward, whatever that plan might be. Open the valve more or something else. But, we touched on engineering. Engineering is such a critical piece to process safety, of course, right? I mean, you've got to engineer the right safety systems. They've got to be sized properly. They've got to be designed properly. Where your process safety leadership comes in and your process safety culture, if they were just relying on an alarm and an operator response, did the operator know what his or her response was supposed to be? Or did they know that that was a critical alarm? Did they know that their response was the only thing between high pressure event and a pressure release, like what occurred here? Did they know that? Because if they don't know that, if they think it's an alarm just like the alarm over here where I just have to, acknowledge it and then rely on my trip, then obviously they didn't have the knowledge, the tools that they needed to respond correctly. So that's process safety key information right there. The design with the horizontal, that's very surprising. I'm surprised that made the design. But again, did the operator know that? Obviously, there was a gap in knowledge of the layers of protection because the operator thought that it was rated for the same pressure as the other reactors. These things should be documented in a procedure, very clearly visible, ideally. But at the same time, this is where that stop. Let me look at my equipment that I'm about to operate, see what my layers of protection are. It's so key to have that information fresh in your mind before you perform an operation like this, where so you don't have to make assumptions, like you said.
Yeah. And at this stage, there's loss of primary containment. It's too late. We're already, we're already in the mitigation hazard control situation versus prevention. So we're definitely on the wrong side of this. Let's keep.
Soon after, a nearby welding machine likely ignited the vapor and a large fire erupted. 23 people were injured, many as they urgently tried to evacuate. The ethylene-fueled fire stopped after approximately 3 minutes when the emergency relief valve closed as pressure in the reactor normalized. In total, over 2,000 pounds of ethylene was ejected to the atmosphere. For more information, visit csb.gov.
Going back to what we call our Safe Energy Ops Leadership Framework, you can get access to this in the link below. We have 3 phases to get process safety leadership, right? And one of those key components is promote safe execution. So it's the ability to stop, assess.
Yeah, so stop and ask what can go wrong, assess your layers of protection, fix any safety gaps that you find during that assessment, and then escalate as needed. So if you can't fix your gaps right there on the spot or with the tools you have available, you've got to escalate. You've got to escalate and say, hey, look, I don't think we have enough layers of protection here, whether that's because one of the layers of protection is out of service, such as a pressure relief valve, or a process safety high pressure trip. For example, we don't know in this particular case if there was a trip function and it just didn't work, or if there was never one designed, but that would be an example of where, hey, look, our pressure safety high trip is out of service. I don't think we should start up this reactor.
So if you guys want to, anybody that's watching this want to download our promote safe execution cheat sheet, take a look at the link here below. Here's kind of the basic steps around how to get that done. And if you'd like some help, implementing this for your site, also make sure to take a look at the links below. You can schedule a free strategy call to see how we can maybe help you in your process safety leadership framework journey.